There's this guy. You see now the participants is right there. So give it.
They are. All right. And they're about to start. So. Oh my goodness. Okay. Okay. Talk to you after the lecture. Bye-bye.
We'll let the Zoom spin up another minute and then we'll get started. All right, well, we'll get started. Good evening. I'm Mark Marley, the director of the Lunar and Planetary Lab. Thanks so much for coming to our third and final public lecture of the fall semester. I recognize some of your faces have been here for all three of the lectures, so thanks for supporting our lecture program. If you're a student that's here for extra credit for a class, the folks, when we're at the end of the lecture, the folks manning the table just outside can put a stamp on your notes so you can see them afterwards. If you're not signed up for the LPL lecture series and LPL events information, you can also sign up at the desk upstairs, at the desk outside. Our next big event is the Art of Planetary Science, which is a entirely student-led art show. It's really nicely done job. There's art submissions from all over the country, from professional artists, amateur artists, all on the theme of planetary science. And it's really well worth coming to see. And that's going to be February 17th to 19th. So, sign up and you'll get reminders about that great event in February. Tonight, it's my pleasure to welcome the newest member of the LPL faculty, Dr. Sukrit Ranjan. He is an assistant professor who just joined us. He's interested in the chemistry of atmospheres, planets with surfaces and their atmospheres, and has done a lot of great work on understanding how planets get their atmospheres, what different chemicals we can find in them, and he'll be telling us about that tonight. Sukrit got his bachelor's degree from MIT and his PhD from Harvard in 2017. He's had a number of prestigious fellowships, postdoctoral fellowships after that, including back at MIT and at Northwestern University. And we were very pleased to welcome him to join LPL in September. And so let's hear life as a planetary phenomenon. There'll be time at the end for questions, and we'll also take questions from the folks online at the end of the talk. So take it away.
Thank you very much for that great introduction, Mark. So LPL public talk aficionados will have noticed a theme to this semester's public talks of exoplanets. Our very first public talk this semester was from Professor Pascucci, who explained to us about how these planets formed. Our second talk was by Professor Ty Robinson, who explained to us how we detect these objects, how we find them, and how now and in the future we're going to figure out what they're made of, and especially their atmospheres. In today's talk, I'm going to tell you about how we hope to use exoplanets to answer the question, two of the oldest questions facing humanity. Where did we come from? And are we alone? When I say oldest questions facing humanity, I really do mean it. Actually, if you go back into the attested literature, the first reference that I found was about 2,000 years ago from this chap named Lucretius in the ancient Roman Empire, 1st century BCE, who wrote the surprisingly prescient argument over here. And if the force of nature remains the same, to throw the wandering elements to and fro, in the same way as here, it must be admitted, there are other worlds and other parts of the universe and other races of men and wild beasts. Put simply, they're making an argument that, to be honest, is still made at scientific conferences today. The laws of nature should be the same throughout a very large universe. If those laws of nature were able to give rise to a world here and life on it here, then they should surely be able to do the same elsewhere. And this argument and variants on it have been deployed by various cultures throughout the ages, but they all boil down to this same basic principle of mediocrity argument. So this has remained in the realm of philosophy for a long time. This has remained in the realm of philosophy for a long time, but about 5 centuries ago, it started to transition into the realm of science, when the first astronomers started to turn their telescopes on the sky, started to surveil the heavenly bodies within our own solar system, and started to see the planets not just as points of light, but as legitimate worlds resolved in their own right. So this was kind of the first kind of affirmation of these predictions that have been made on philosophical bases by sages throughout the centuries, that there are other worlds out there, which naturally gave rise to the next question: are there other, as they said, races of men and beasts out there? Are we alone in the cosmos or not? And this is a question that really motivated people, and the kind of the first effort to really constrain the existence of extraterrestrial life actually was substantially led by folks here in Arizona, in the form of the so-called Martian canals. So in the 1800s, as telescopes advanced, we began to start to see Mars not just as a bright point of light, but as a resolved disk. And we began to map the surface of Mars. And some astronomers within those maps identified regular linear features, which they began to interpret as potential physical features that were so straight that they could only reasonably be due to being architecture, to being constructed. And in fact, they were interpreted as evidence of canals. Arizona has a particularly strong role to play here, because the foremost proponent of this hypothesis was our own Percival Lowell, who carried out his observations right here in Arizona. And he responded to criticisms from other astronomers that they couldn't reproduce these features with the argument that, well, you're observing out in the East Coast or out in the old world with polluted skies. Come to the clear, pure mountain air of Arizona and you'll see much more clearly. And this was actually an area of scientific debate all the way up until the 1960s, where this debate was put to rest by the first probes to visit the red planet. These probes, starting with orbiters like Mariner, all the way to rovers like Curiosity and Perseverance, revealed a fascinating world, one with all sorts of interesting physical processes going on and a rich history, including our largely wet past with significant amounts of surface liquid water. However, what they did not reveal was a world that was alive in the biological sense. While there may still be life on Mars, hidden in the deep subsurface where conditions are clement, the surface of Mars is largely desolate. It is not an inhabited world like the astronomers thought back in the 1800s. And unfortunately, this trend has repeated itself again and again in our surveillance of the solar system. For example, astronomers once looked to our sister planet Venus and saw a planet closer to the sun than our own and swaddled in clouds, and imagined that it was a swamp planet, that it was warmer than our own planet, wetter than our own planet, but still very much alive, full of vegetable life, and perhaps even reptilian life, analogous to Cretaceous Earth. Regrettably, the first space probes to Venus also put a kibosh on this picture. They revealed a world that was fascinating in many ways, but whose surface, for sure, was firmly 100% uninhabitable. Temperatures and pressures sufficient to melt lead, way drier than the Sahara Desert by many orders of magnitude. It was not a swamp planet pregnant with life. It was not. And as we've explored the solar system with a number of these wonderful probes, we've discovered so many beautiful exotic worlds. We've discovered a diversity we could never have imagined just from staying here on Earth. We've discovered clouds made of substances as diverse as carbon dioxide crystals, sulfuric acid. We've discovered worlds swaddled in water and other worlds covered in lakes of liquid hydrocarbons. But one thing we haven't discovered is Earth 2.0, we haven't discovered specifically an Earth-scale biosphere elsewhere in the solar system. Now, that isn't to say that the solar system is necessarily uninhabited. There's still the possibility of so-called cryptic biospheres, small trace biospheres that cling to life in habitable niches within the bodies in our solar system. But there's no globally clement abode for life beyond Earth, and there's no global biosphere beyond Earth. And that was the state of affairs for quite a few decades. The state of affairs finally started changing about 30 years ago with the discovery of so-called exoplanets. Oh no, there's sound. I didn't want there to be sound. Go away, sound. Okay. With the discovery of so-called exoplanets, planets orbiting stars other than the Earth. The first exoplanets found were completely uninhabitable in the sense that they orbited a dead star, a neutron star, a pulsar. But soon after that, people started, the first exoplanet orbiting a main sequence star similar to our own sun was reported. Initial discoveries of that were sharply questioned, and there was a lot of back and forth. But as surveys accelerated, as we started observing more of these planets and getting more and more corroborations, it became clear that not only did exoplanets exist, but there were a lot of them. And this kind of trickle of exoplanet discovery turned into a stream and then a flood with the advent of the Kepler mission and the TESS mission, which turned our count of the exoplanets from the dozens and the hundreds into the thousands. Today, over 5,000 exoplanets are known, which begs the question, if this will advance. Who leaves this? No, go away. Which begs the question, amongst this cornucopia of worlds, is there another Earth out there? Is there another globally clement planet with a globally present biosphere that we could recognize, containing life that we could recognize as being in some way similar to our own? Astronomers are just as motivated by this question as everyone else, and planetary scientists. The fundamental tool that we've used to start to guide our search is the idea of so-called potentially habitable worlds or temperate terrestrial planets. The idea is this: there's two kind of broad conditions we know are almost certainly required for habitability. The first is getting the right amount of sunlight. If you get too much sunlight, you end up being too hot. You end up being so hot that you vaporize all your water vapor. It goes into the atmosphere and triggers a runaway greenhouse, and you end up like Venus. If you're too cold on the other hand, all of your water freezes out, and you end up more like Enceladus. Size is also a really important parameter. If you're too large a planet, your gravitational field is too strong and you'll hold on to lots of hydrogen and helium. You'll end up being more like Neptune or Uranus than Earth. If, on the other hand, you're too small, your force of gravity will be too weak. You won't be able to hold on to your atmosphere, and you'll end up a little bit more similar to Mars. So there's this idea that in order to be potentially habitable in the same way that Earth is globally habitable, you need to be kind of an intermediate size, and you need to have an intermediate amount of light from your host star. And building off of this, scientists here at the University of Arizona and elsewhere have put a lot of energy into trying to figure out just how many of these potentially habitable planets are there. The number in the literature has bounced around a lot, but overall in the last few years, it seems to be converging at about the 10% level. So 1 in 10 stars has a potentially habitable planet orbiting it. This is in some ways a little bit disappointing. I mean, 90% of stars don't have habitable planets. But on the other hand, to me personally, this was incredibly exciting because there are so many stars in our galaxy and even in our solar neighborhood. This means that our galaxy has billions to tens of billions of potentially habitable planets. And there should be dozens of them within our own stellar neighborhood. And in fact, the statistical expectation based on kind of the census reasoning has been confirmed by experimental discoveries, observational discoveries of numerous potentially habitable planets. In fact, the closest star to our own sun, Proxima Centauri, hosts a potentially habitable planet, Proxima Centauri b. And this reality that the universe is filled with potentially habitable worlds has catalyzed a new spurt of philosophizing about life in the universe and what it might mean. There's an Arizona connection here. Back in 2009, no less an institution than the Vatican convened a scientific symposium to confront the possibility that extraterrestrial life might be out there. It might be discovered in the next few decades, and what that would mean theologically and sociologically. Here too, the University of Arizona has played a key role. The director of the Vatican Observatory, who's deeply engaged with these questions, got his PhD right here. and still continues to do observations and so forth out here. So this is hometown question, hometown work we're doing. But this is all well and good. There's a lot of potential abodes for life out there, but how the heck are we ever going to see them? I mean, life is tiny, it's the size of a cell. And these planets are separated from us by distances of tens of light years or hundreds of trillions of miles. So how the heck are we going to see something as small as life from so far away? Well, the basic approach we're going to do this gets back to the title of this talk. We're going to exploit the fact that life is a planetary phenomenon. And that means that life is shaped by the planet that it inhabits, but equally the relationship goes the other way. Life can also profoundly affect the planet that it inhabits. In fact, our own Earth has been irrevocably, irretrievably altered by biology, from the colors of its continents to the oxygen in its atmosphere. And it's this kind of large-scale biological modification of the planetary environment that is potentially remotely detectable and that we hope to find. This kind of qualitative, airy-fairy picture that I've outlined to you was first put on quantitative footing by the so-called Galileo experiment back in the 1990s. This was a rather creative experiment. So on its way to Jupiter, the Galileo space probe, also with LPL involvement, did a flyby of Earth. When it did its flyby of Earth, a group of scientists led by Carl Sagan got together and creatively pretended that they were not human. They were in fact aliens, and that Galileo was their interstellar space probe visiting a potentially habitable planet. And they asked, purely on the basis of remotely detectable evidence, purely on the basis of things they could measure from Galileo space probes, space instruments, could they infer whether or not Earth was a habitable planet? And they took their measurements and they came up with this really gorgeous spectrum, which many of us will salivate if we ever get anything near it from an exoplanet. And with this excellent quality data, the answer they came up with was a resounding, probably. The specific line of reasoning they executed was as follows. They took the fundamental observations from Galileo that Earth was rocky, probably temperate based on climate modeling, and that its spectrum had signs of water vapor, oxygen, and methane. These last two were particularly exciting to them because as anyone who's turned on a gas stove in their house knows, methane and oxygen mutually annihilate given the chance. So in order to have a significant amounts of both of these gases, you needed to be producing them at the surface in very large quantities. They then did an exercise. They said, all right, fine, we found something weird in the atmosphere of this planet, but how weird is it really? And so they set out to ask, based on their understanding of how planets work, based purely on their understanding of planets and not being specific to Earth in any way, could known planetary mechanisms explain the inferred levels of oxygen and methane? And the answer they came up was not really. Planets would have to work in fundamentally different ways for an abiotic explanation to work. All right, but does that mean it's necessarily biology? The next question they asked was, is the planet habitable? Is biology a viable hypothesis in this particular context? The answer they came up with was yes. And their argument was fundamentally premised on the existence of water vapor in the atmosphere, coupled with the fact that the planet should be temperate. That means that in order for water vapor to be present in the atmosphere, there needs to be a lot of liquid water also present. So liquid water is the main ingredient for a main requirement for life as we know it. Therefore, they concluded the planet was habitable. Therefore, life was a viable hypothesis to put forward. So why wasn't this a slam dunk then? The answer is slightly counterintuitive and goes into the depths of chemistry, which to me as someone with a physics background is always something that's deeply scary, but you got to do it anyway. So let's do it. If you ignore what you know about modern biochemistry, if you ignore what you know about modern life on Earth and just look at the biochemical fundamentals, the idea of organic life and oxygen is totally whacked. And the basic reason for this is that carbon in our biology is in a reduced form. If you have free oxygen present, it tends to produce so-called oxidative free radical species, which attack those biomolecules and destroy them fairly efficiently. In fact, so you might be asking, well, how can this possibly be the case? Oxygen is essential for me. If I go without oxygen, bad things will happen in a very short time scale. And the answer is that you and I are equipped, you and I and other oxygen breathing or anaerobic life, or aerobic life is equipped with an incredibly sophisticated biochemical apparatus that's capable of processing this poison and even using it. A series of incredibly sophisticated detoxifying pathways that can take those oxidizing species and neuter them, turn them into something that's not harmful for us. This, by the way, is why folks who are into health foods will often talk a lot about antioxidants. Those are chemical species that you can eat that are supposed to help promote these pathways, that are supposed to help inhibit these free radicals. And so this is why when Sagan et al. Made their publication in Nature and they made their final inference about whether or not life was present, they had this giant question mark about, well, everything's pointing to life, but it's in a bath of O2. How plausible that is, you tell me. So that kind of big caveat aside, they were really trying not to be terracentric here. That big caveat aside, this still gives us kind of a recipe for remote life detection, which guides our efforts to this day. The recipe is, first we're going to do measurements. We're going to go out and figure out what these planets were made of. We're going to figure out what their bulk planetary parameters are. We're going to figure out what their star is doing. And most critically, we're going to figure out what their atmospheres are made of. Then we're going to ask if there's something weird there. We're going to ask if there's any gases present that we know are made by biology. We're going to ask if known abiotic mechanisms can explain that flux. So first and foremost, we're going to play devil's advocate, and we're going to work as hard as we can to make abiological explanations explain the measurements that we have. Only if the answer is no will we proceed to the next step, which is asking, well, all right, abiotic mechanisms don't seem to work very well. Could biological mechanisms be plausible here? And if the answer to that question is no, then we'll have a probabilistic constraint regarding the presence of life. You might be saying, well, this is all well and good, but the very first step of this entire logical chain is doomed to fail. Now you're telling me that we need to take these stars hundreds of trillions of miles away and measure the abundances of trace gases in their atmospheres? That itself seems ludicrous. And I would have agreed with you. Fortunately, my observational colleagues are much cleverer than I am and have figured out ways around these remarkable challenges. And one of the most significant paths folks have figured forward is exploiting these so-called transiting exoplanets. Transiting exoplanets are planets which, from our point of view, appear to pass in front of their host star. When they do so, some of their starlight is going to filter through the planet's atmosphere. It's going to filter through the annulus of that planet's atmospheric absorption. And in our last public talk, we learned about how when light passes through a gas, the elements of that, components of that gas can absorb some of that light in selective ways. They can alter the color of that light. And the way those colors are altered can be diagnostic of different molecules. So by carefully measuring the color of the light coming off the planet, we can figure out what the planet's atmosphere is made of. This remarkable technique has been deployed to great effect. With exoplanet spectroscopy today, with instruments like the Hubble Space Telescope, we can detect molecules like water vapor and atomic features like sodium and potassium in the atmospheres of giant exoplanets, planets the size of Jupiter and Saturn orbiting other stars. However, I've lied to you. I've said exoplanet spectroscopy today. And that is, of course, not true. This is exoplanet spectroscopy yesterday, a year ago. Today, we have the James Webb Space Telescope, Hubble's successor. And while Hubble was great, James Webb blows it out of the water. This is an example of some early release science from the James Webb Space Telescope, work done by some of the astronomers here at the University of Arizona. And well, this is a detection of carbon dioxide, the first high confidence detection of carbon dioxide in an exoplanet atmosphere. And it is just exquisite. I mean, I want you to look at the error bars over here and the density of the points and compare them to that spectrum over here. There's no comparison. James Webb is a transmission spectroscopy machine. With only a small amount of observation time, it can robustly detect a wide range of molecules in the atmospheres of giant planets, which begs the question, maybe, just maybe, in the most favorable situations, it can do the same. It can also detect some molecules in the atmospheres of smaller, rocky, potentially habitable planets. And this is something that the astronomical community actually believes is possible. They believe so deeply that it's possible that they've decided to stake the future of the field on it. Every 10 years, the astronomical community gets together and decides what are going to be our scientific priorities for work over the next decade. What should we be prioritizing? And the priority that was identified as the highest focus for space missions was the development of a space telescope that is capable of robustly measuring the atmospheres of small planets orbiting stars other than our own in search of signs of life. And this is happening now. It isn't science fiction. It isn't a possibility. It's a commitment. The James Webb Space Telescope is now observing some of those most favorable targets already, with the objective of hopefully detecting molecules in their atmospheres. And the next, In the next decade, the extremely large telescopes, ground-based telescopes, will come online and will augment our capabilities still further. And then 2 or 3 decades down the line, we can hope to see this mission concept that's being articulated over here, what many of us are calling LUVEX, that might have the capability of not just getting the most favorable targets, but really getting a number of targets and really getting giving us a deep, comparatively speaking, deep sample relative to the small numbers we're talking about over here. Okay, so provisionally, let's accept that we're going to do step A. Let's accept that we're going to get measurements of the atmospheric composition of these exoplanets. What next? Are we going to be able to make into these next steps? That's one of the things that I'm really interested in focusing on. That's where a lot of my research program ends up dialed in on. So one of the first things we're going to need to do once we have these spectra, we're going to have to look for something weird, something that might be a signature of life beyond Earth, a so-called biosignature gas, which means that first we need to identify what biosignature gases are and what their false positives are. And we can approach this in a systematic way. We can write down a wish list. We can say, what are the features of an ideal biosignature gas? Well, it would be spectrally distinguishable. It would have a clear and distinctive spectroscopic fingerprint, color fingerprint that we could use to tell it apart from other gases. Ideally, it would have no abiotic false positives. Life should be the only things that makes that gas in any quantities. You don't want it to be able to be spoofed by processes like lightning, volcanic activity, and so on and so forth. And ideally, it should not be invisible, by which I mean it should be plausible for it to accumulate to detectable concentrations in the atmosphere of an extrasolar planet at biochemically plausible production fluxes. Regrettably, the perfect biosignature gas has not yet been identified. A lot of work on biosignature gases is focused on so-called metabolic byproducts, gases which are produced as a consequence of life's harvesting energy for its own use. These gases have a common story to them. They're really strongly biochemically motivated. They're produced in abundance by our own biosphere. There's a strong incentive for them to be produced by alien biospheres as well. But the big challenge with them has been that a number of false positive mechanisms have been identified that produce them. So life is able to really robustly produce these gases, but it turns out that some abiotic processes are also able to exploit these chemical gradients that life gases, and as a consequence is able to generate, in some cases, a false positive for some of these. The elephant in the room that we have to confront is oxygen. Oxygen is the most important, the most compelling biosignature gas candidate we have. And that's just because of how profoundly it's altered our own planet's atmosphere. So at the beginning of Earth's history, around 4.5 billion years ago, Earth's atmosphere is anoxic. There was at most a 10 millionth of the amount of oxygen we have in our atmosphere, and probably only about a trillionth of the oxygen we have in our atmosphere. This remarkable state of affairs was changed by the advent of biology, which invented the process of oxygenic photosynthesis, which is summarized in this reaction over here. So you take what life does is it takes carbon dioxide and water. It takes free energy in the form of sunlight, solar photons, 8 of them, at least, sometimes it's less efficient, but at least 8 photons, and it combines them to make fixed carbon species, which both accomplish structural functions, use them to build cells, and they also accomplish energetic functions, provides chemically usable energy. And oxygen is just a kind of waste product that dumps out of the atmosphere. This waste product has had profound effects on our atmospheric state. And over the last couple of billion years, it's risen from being basically absent from our atmosphere to absolutely dominating its atmospheric state. Today, the Earth's surface atmosphere system is completely dominated by oxygen. Not just the air, but the rocks have been changed by it. Unfortunately, the very same things that make oxygenic photosynthesis so incredibly compelling as a metabolic pathway are also underlie its challenges as a biosignature. The reason oxygenic photosynthesis is such a compelling metabolic pathway is it takes 2 of the most common substances in a planetary environment as its substrates for its chemical reaction. So CO2 is the main carrier of carbon in our planet's atmosphere. H2O is the main carrier of hydrogen in our planet's atmosphere, in our planet's surface. And it combines those 2 incredibly common things to extract energy and produce biomass. So that's incredible. It's a biochemical home run. But the challenge is both of these molecules are really abundant, and it's possible for abiotic processes to operate on them to give rise to oxygen as well. All oxygen false positives fall into one of two categories: escape-based or photochemistry-based. Escape-based rests on the fact that this water vapor substrate, if you irradiate it with UV photons, it tends to convert to hydrogen gas and oxygen gas. Hydrogen is super light, so it can escape out the top of the atmosphere. It can escape to space, leaving behind oxygen. And if you can conceive of planetary scenarios in which this process would be efficient, so efficient as to leave behind detectable quantities of oxygen. The second broad family of false positives is photochemically based, and specifically CO2 photochemically based. If you take that CO2 and you combine it with starlight, that too tends to photodissociate and give you carbon monoxide and oxygen atoms. The reverse reaction is inhibited, it's spin forbidden, quantum mechanics doesn't like it, so we can't do it. Instead, what can tend to happen is that those two oxygen atoms can react together to give you molecular oxygen, which can also accumulate. And so a lot of the work over the past decade and a half is focused on really trying to understand what are the planetary scenarios in which one or the other of these mechanisms can operate and give you a false positive for O2. And what are some of the mechanisms by which we can differentiate them out. And the overall consensus for oxygen is that we're going to need to see something else. We're going to need to look for other species to either corroborate that oxygen is a biosignature or to rule out the possibility of these abiotic false positives. And that's something we can do, but it's going to require more observations and getting multiple gases. Broadly, you might ask, what about some of these other gases? Like, for example, what about methane? The problem that's been raised for gases like methane in the past is that a whole bunch of processes can, other than biology, can generate it as well. But there's a potential pathway around this. It's true that a broad range of processes can generate abiological processes can generate methane, like all the ones over here. But what these processes can't generate is enormous, gigantic quantities of methane. There's upper limits to how efficacious they can be. So if you specifically detect a gigantic amount of methane in an exoplanet atmosphere, one that implies a really high production rate, then methane can be a robust biosignature. Folks have also looked at N2O as a biosignature, the laughing gas, and the story is pretty much the same there. There are false positive mechanisms for N2O. So if you detect intermediate amounts of N2O, it's going to be a little bit challenging. But if you specifically discover lots of N2O in a temperate terrestrial planet atmosphere, that is a lot harder for abiotic mechanisms to spoof. So if you can detect a lot of these last two biosignature gases, that could be something that's potentially very suggestive. But some folks aren't satisfied with this discriminating out abiotic false positives. They always worry that there's going to be some kind of like fine print we haven't checked, and and maybe you won't be able to rule out that possibility. So this has led to the search for biosignature gases that might be completely robust to false positives, that have very low false positive potential. And the main candidate that's been suggested in this regard are the so-called metabolically expensive biosignature gases. These are gases that life does not produce in order to harvest energy. In fact, making them consumes energy, and it's often detrimental to the cell in other ways. The reason biology produces these is to dissipate waste or to accomplish secondary functions like signaling. But the bottom line is that they're so energetically expensive to make that it's relatively hard for abiotic processes to make them as well. There's a common story you can tell for these gases as well. Their spectral features tend to be pretty reasonable. Their known false positive potential is comparatively limited, but they're violently reactive. They fall apart at the touch of a feather. They fall apart if you shine light on them. They fall apart if you touch them with a radical. They fall apart if you breathe too hard on them. And the bottom line is for planets orbiting sun-like stars, planets similar to our own Earth, at biochemically plausible production fluxes, they just do not accumulate to detectable concentrations. They're invisible. Fortuitously, not all stars in the universe are like our own sun. Actually, our own sun is a little bit exceptional, as summarized in this plot here from the Recon survey. So here I'm showing the 100 stars closest to our own sun. And what I want to point out is that yellow stars, like our own sun, are actually somewhat anomalous. They only comprise on the order of 10% of the stars in the universe. Most stars in the universe, about 75%, are these small, cool, red M-dwarf stars. And these M-dwarf stars, once derided as the vermin of the skies, actually have a really important stellar physical characteristic which makes them uniquely favorable for detection of atmospheric biosignatures. They emit very little UV light. They emit so little UV light that it's possible for these even these reactive biosignature gases to build up to much higher concentrations. And in fact, if you look specifically at planets orbiting these M-dwarf stars, it turns out that at biochemically plausible production fluxes, it is possible for these gases to become detectable. But some people, but you'll notice I have this word low here for false positive potential. And some people still aren't satisfied with that. They really want 0. So what are potential signposts of life beyond Earth that really have 0 false positive potential that you couldn't conceivably imagine nature making? Well, one extreme you can take this to is saying, really, let's not look at anything that nature makes. Let's specifically look for the products of a technological civilization that no process, biotic or otherwise, no non-technological process, biotic or otherwise, makes. And there are several such candidates. They fall into 3 broad families. One family are artificial molecules, things like CFCs on Earth or SF6, things that we have detected nowhere else in nature or in biology. So if you observe CFCs in the atmosphere of an oxygen-rich planet, to me, that would start seeming a little bit suggestive. So I'll give them that one. Another clever idea is looking for evidence of artificial lighting. In particular, the more efficient kinds of artificial lighting we use these days, like LEDs, also have a characteristic absorption emission spectrum. They have a characteristic kind of light they give off, just like gases do. And so one idea is to look for those gases, in spectra as well. And the compelling thing about this idea is you can do it at the same time as you're looking for more conventional microbial gas biosignatures. You don't have to build a special instrument or anything like that. You get it for free with a regular biosignature search. And of course, the third major class of technosignature you can look for are radio waves. You can look for basically alien, I Love Lucy, alien radio signals, alien TV, leakage from a technological civilization. That's something that SETI has been working on for quite some time and has recently been revamped to pursue in more detail with private funding sources. One other thing I couldn't resist popping in is look for not just a planetary scale technosignatures, but really stellar scale technosignatures. And this is an idea that goes back to the 1960s, the idea of a Dyson sphere. And theorists, some people just perhaps were thinking, what is the end state of our own technological civilization? What might technological civilizations evolve to given enough time? Well, one thing we know technological civilizations want is they want energy. The biggest source of energy any civilization growing up on a planet have is their star. But most of that starlight is just wasted. It just goes off into space and people on other planets can look at it and it twinkles and stuff like that. Completely useless. So what they speculated is maybe a sufficiently advanced civilization will enclose their star in a structure and harvest that energy, a so-called Dyson sphere. Well, it turns out that this also would have a characteristic signature. It would give you this kind of M-shaped feature in IR spectrum. And this is also something you can look for kind of for free, because it turns out that astronomers build satellites to do IR infrared surveys all the time. And in the process of trying to measure this spectrum, you can just look to see if there's an M-shaped spectrum as well. And people have actually done this. People have gone out and looked for these signals and placed a whole bunch of upper limits. So we haven't seen anything. Sorry, no Dyson spheres yet, no alien megastructures. But what we have been able to do is use this upper bound in a useful way. We've been able to say that this picture of kind of the broad scape of technological civilizations that was being outlined in the 60s is incorrect. The galaxy is not full of species with building Dyson spheres everywhere. And so even a non-detection can teach us something useful. And this kind of gets to the last point I want to make in this public talk. What happens if we don't see anything? What happens if we build these gorgeous space telescopes and we go out and we work super hard and we collect these spectra and we get beautiful spectra of planets orbiting other stars, rocky terrestrial planets orbiting other stars. And on the life question, we hit a blank. We don't see any convincing biosignatures. We don't see any good evidence for life beyond Earth. Have we wasted our time? Have we made no progress in our quest to understand life as a planetary phenomenon, life in the universe? I would argue that's not the case. I would argue that regardless of whether or not you detect a biosignature, studying rocky planets or other stars can tell you a lot about life as a planetary phenomenon, because it can help you understand the origin of life. One of the things that for the past 70 years, chemists have been trying to figure out how life got started. They've been trying to simulate early Earth in a bottle, early Earth in the lab, and ask how could the molecules that were present there have come together and chemically complexified to give you something you'd recognize as alive. And the major problem they've hit is they don't really know what early Earth was like. They don't really know what to simulate in the lab. They can't get a high fidelity simulation. And the basic reason for that is the habitability of our planet. It's a double-edged sword. Yes, it lets us exist, but it doesn't let us figure out how we got here. More specifically, our planet's active hydrological cycle and our planet's plate tectonics, which are so important for our being alive, destroy rocks from early Earth. We have very few messengers left from 4 billion years ago. What we have are tiny, not even rocks, but tiny fragments of rocks, like small zircon crystals embedded in much older rocks, or bits of organic gunk left over from 3.5 billion years ago, which we can analyze isotopically and make very coarse, crude statements. We can then take those coarse constraints and plug them into climate models. And plug them into various theoretical models, and we can get a somewhat quantitative, but really mostly qualitative picture of how early Earth was like, that we can then use to try to guide guide our laboratory studies of origins of life chemistry. And this is better than nothing, and we can even put error bars in some of this stuff, but really what we're doing is flapping our arms really quickly and hoping we're trying to fly. We'd like to do better. And this is where one of the really important parts about exoplanets comes from, is that many of these exoplanets orbiting other stars might be like early Earth. In particular, if you detect a planet without a biosignature, there's a possibility that it's an abiotic world like early Earth, which means that observations of exoplanets may give us our best opportunity to see what early Earth was like, to see the palette of environmental conditions that was available, the diverse molecules that processes like impacts and volcanic activity and photochemistry could generate. And this means that by studying habitable but uninhabited planets, we might get our strongest constraints yet as to how our own habitable planet became habited. Another way I want to point out in which non-detections constrain our understanding of origin of life or theories of abiogenesis is really directly. Let's suppose, for example, you detect life on one type of planet, but not another. That hints that that type of planet has a certain environmental condition that's required for life, which others don't, which gives you an inkling as to what the environmental conditions for the origin of life are. One of the things that I and others have been working on in particular is UV radiation. It turns out that there's many families of origins of life chemistry that require UV radiation in order to proceed as a source of chemical selection and free energy. And those low mass stars I was telling you about earlier, those M dwarfs, they don't have very much UV. So if you don't detect life on planets orbiting these stars, and you do detect life on planets orbiting more sun-like stars, that's a hint that maybe UV is essential for the emergence of life. So that's another way in which non-detections can help us. But let's suppose we totally hit a blank. Let's suppose we don't detect life on so-called Earth twins as well. That's totally a possibility. We're reasoning from one data point here, us. And that actually also tests a theory. It tests the rare Earth theory. The rare Earth theory is a way to try to explain how hard it is to make life in the lab. And it says maybe the origin of life is just hysterically unlikely. Maybe in order for life to get started, a bunch of molecules have to quantum tunnel in just the right way, and in some hysterically unlikely way, they come together and they make a self-replicating biomolecule, and that's what has to get everything started. That's possible. But if that's the case, life is a fluke, and you don't expect to see life anywhere else in the cosmos. So if we really do, in the distant future, probably my children's children, build solar gravitational lens telescopes and survey every star and see no evidence of any kind of biosignature, maybe that is a hint that that at long last we found a way in which humans really are unique, in which we are a privileged part of this universe. I'd like to end my talk here and just present my key summary points. Temperate rocky planets, or potentially habitable planets as the buzzword is, orbiting other stars are common, and we will measure the atmospheric spectra within the next 10 to 30 years. And I'm just so happy to be able to say that. We weren't able to say that 2 years ago. We will search these worlds for evidence of life by looking for planetary scale biogenic modification. Life is a planetary phenomenon, and especially planetary scale modification of their atmospheres. To succeed in this search, we have to do a considerable amount of work right here in our solar system and right here in our labs. We have to understand what potential biosignature gases are and what are ways in which abiotic processes like lightning, impacts, volcanism, and so on and so forth can spoof them, the so-called geophysical or cosmochemical false positives. And even if we don't find nothing, it doesn't mean our effort will have been wasted. Even non-detections of exobiology and studies of non-living planets will strongly inform our understanding of life in the universe through our understanding of how life got started. I'd like to leave you with this surprisingly philosophical quote from an otherwise what I personally perceive to be an extremely bureaucratic committee. Sorry, Mark. Which is life on Earth may be the result of a common process, or it may require such an unusual set of circumstances that we are the only living beings within our part of the galaxy or even universe. Either answer is profound. The coming decades will set humanity down the path to determine whether we are alone. Thank you for your time. I'd love to take questions.
Well, thanks very much for that great whirlwind talk on thinking about how we're going to find and characterize life out there in the universe. Do we have any questions from the audience? Back in with the hat, we'll start. Go ahead.
Yeah, tell me a little bit about nitrogen. If somebody looks at Earth, they're going to see like a whole lot of nitrogen and then like a little bit of oxygen and other things. Is nitrogen like part of our history or present or any of those things?
That is a great point. So the first order, if someone looks at Earth, they will not see nitrogen. And the reason they will not see nitrogen is that despite the fact there's so much of it, it's the most abundant gas in our own Earth's atmosphere. It's basically optically inert. It absorbs only in the very, very deep UV, and otherwise it essentially doesn't interact. It's very, very hard to see nitrogen. The one case in which this is not true is if you have a lot of nitrogen present. And if you really have a lot of nitrogen present or other gases present, they can interact with each other. They can create so-called collisionally induced absorption or nitrogen-nitrogen dimers. And if you can detect those species, then you can get some constraints on the abundance of nitrogen. But you'd either need a really, really good telescope, like better than the one we have coming in 30 years, or you'd need a really large amount of nitrogen.
Okay, cool.
Yeah, it's funny, the nitrogen's so common, but yet we can't see it.
Yeah, thanks for the great talk. I'd like to hear more about your thoughts on the relationship between biosignatures and technosignatures. Do you think if one is like necessarily indicative of the other? And also in our universe, what do you think might be the most likely technosignature?
Good questions. I need to think a moment. I would say that I personally am greedy. So the more potential signs of abiotic modification I can see, the more excited I am. I think the gold standard in the biosignature paradigm is to detect multiple biosignature gases. For example, what everyone wants to really detect is both methane and oxygen. It's just that there's some debate about whether or not we can do that. Mainly because it turns out that at least in Earth's history, when you had a lot of methane, you had very little oxygen. When you had a lot of oxygen, you had very little methane. And it's just a remote detection problem. So I would say that if we can get them both, we're going to sing and dance and be super happy. But yeah, we don't see it as an either or thing. In terms of most common technosignature, I really have no idea. Like, I think before I started thinking about this, I would have all sorts of ideas. But then I've learned a lot about how if you have no data to constrain off, you get out your priors. And our priors aren't really founded on very much right now. So I don't think, yeah. I guess if I had to make a statement, I would say that I wouldn't look for intentional beaming. I wouldn't look for civilizations to try to actively communicate with us because I don't see the point for them doing that. I'd look for evidence of them pursuing their own self-interest in some way.
Do we have any questions online, Amy?
No questions right now.
Okay, thank you. Any other questions from the audience? Yeah.
So I have a question on how were the false positives discovered while observing the atmospheres of distant exoplanets, and how can we distinguish false positives from real or accurate signs of life if spectral observations can be flawed to some extent?
That's a great question. The short answer is we need to understand all planets, not just potentially habitable planets. So if, in order for us to identify if a gas is potentially due to abiotic means, we need to understand how abiotic processes in planets in the absence of life operate. Fortuitously, we have a number of such objects within our very own solar system, which this lab and others are in the process of exploring in a lot of detail. There's a lot to discover there. We're still learning more about how different kinds of volcanism operate, both here on Earth and in other worlds. There's potential detections of lightning in the atmosphere of Venus, so that's an opportunity to learn more about how lightning in a CO2-dominated atmosphere operates. So within our own solar system, there's a lot we can learn that'll help us interpret these observations of exoplanets. Similarly, many exoplanets, it's going to be really hard to characterize potentially habitable planets, but it's going to be relatively tractable to characterize uninhabitable planets, planets that are, for example, too hot to conceivably host life. And by studying those planets, we'll get a broader sense of how processes like planetary volcanism operate. It will help us constrain potential false positive mechanisms.
This might be silly, but if there was a civilization that was like technologically advanced enough to like create a Dyson sphere, wouldn't they have been able to like find us already? Not that silly, pessimistic, or
That's a great question. The answer is, so you can look at this in a couple of ways. So if you mean by us, you mean like us as a biosphere? Possibly, yeah. If they have a good enough telescope, if they use something like a solar gravitational lens or something, sure. They could see that other planets should be able to see that life on Earth exists. And this has given rise to some actual papers, which I think are largely tongue-in-cheek, about how to build cloaking devices to prevent other planets from seeing us by transmission spectroscopy. If you want to talk about detecting us as a technological civilization, the window for that actually seems to be closing to some degree. To the best of my knowledge, we're already past the period of our peak radio emissions. That's because we've shut down a lot of the extremely active radar that we used to scan for nuclear missiles back in the days of the Cold War. So we're already going down. A lot of our television signals are now routed over cable as opposed to being bounced off the ionosphere. As part of the ecological movement, we're reducing the amount of gases we pump. We're trying to reduce the amount of gases, things like CFCs we pump into the atmosphere. So the signs of our technological civilization to some degree are actually, I would say, going down.
Except maybe for lighting.
Yeah, lighting is still going through the roof. But yeah, with that, if we pursue standards like what Tucson has more, which is more limited outdoor lighting directed downwards, not using sodium lamps, all that kind of stuff, that can help improve that as well.
So yeah, so it depends if the other civilizations or have astronomers around or not. Any other questions from the audience? I'll check just one more time online. Nobody?
No questions.
Thank you so much. Well, thank you everybody online and in person. I'm sure Sukrit will be happy to answer any questions in person. And again, for the students, if you need a stamp, you can get it on the way out. And if you haven't already and are interested, do sign up to be on our in our email list. So thank you really, everybody. We're so happy to be able to fund back up our LPL lecture series this fall. And we look forward to you all joining us again in the future. So thanks very much.